Hi, this is Engineering Statistics and Linear Algebra 18 EC44, Module 4, Lecture 11, Part 2 will be speaking today. That just corresponds to the orthogonal subspaces. I am Dr. Nurullah Sharif, Professor and Head EC Cam Institute of Engineering and Technology. So in the last lecture, which corresponds to the Module 4, Lecture 11, Part 1, orthogonal vectors, we were speaking about, and in the orthogonal vectors we considered the length of a vector and also the test for the orthogonal vectors, which corresponds to x transpose y equal to 0. Two vectors x and y will have x transpose y equal to 0 to be perpendicular or to be orthogonal, and also how to create perpendicular vectors from linearly independent vectors. So we considered here the length of the vector, which just corresponds to the general formula, which is nothing but the length squared is equal to x1 squared plus x2 squared plus x3 squared plus etc. xn squared, that is equal to x transpose x. So length will be naturally the square root of the length squared. So then we took an example and then we defined what are orthogonal vectors, wherein we tried to prove that orthogonal vectors, two vectors x and y are orthogonal only when x1, y1 plus ... xn, yn is equal to 0 or x transpose y is 0. So the proof of that is what we considered, and then we said that 0 vector is orthogonal to itself and orthogonal to every vector in r to the power n. So this will be the standard format. 0 vector is orthogonal to itself and orthogonal to every vector in r to the power n. Then we took up a example of length of two different vectors, and then we took the theorem, which just gives us for if non-zero vectors v1 to vk are mutually orthogonal, that is every vector is perpendicular to every other vector, then those vectors are linearly independent. If v1 to vk are mutually orthogonal or every vector is perpendicular to every other vector, then they're all linearly independent. So the proof of that is considered. Then also we said that the coordinate vectors e1 to en in Rn are the most important orthogonal vectors, and this e1 to en are columns of the identity matrix. They form the simplest basis for Rn, and they are unit vectors. Each has a length of 1, and they point along the coordinate axis. If we rotate these axes, then we will get a new orthogonal basis, and that will just correspond to a new system of mutually orthogonal unit vectors. Also, in R square, we have cos square theta plus sin square theta is equal to 1, and the orthogonal vectors in R square are two different vectors. The v1 equal to cos theta comma sin theta, and v2 equal to minus sin theta comma cos theta. Generally, they are written in the form of, in the matrices, they are written in the form of a column matrix. Now we will consider the part 2, which just corresponds to the orthogonal subspaces. So the what you call subspaces V and W are orthogonal if, again, V small v transpose W is equal to 0 for all V belonging to the vector space, vector subspace capital V, and all W small w belonging to capital W vector space. Or we can say VTW is equal to 0 for all V belonging to the basis of V and for all W belonging to the basis of W. The subspace which corresponds to a 0 vector is orthogonal to all the subspaces. And a line can be orthogonal to a line or a plane. It's always possible that a line can be orthogonal to a line or a plane in a R-cube space, but a plane cannot be orthogonal to a plane in R-cube space. So this just gives us that are the front and side walls of a room orthogonal to each other. So the answer for this is we see that whether we need to check whether there is something common between the front and the side walls. So between the front and the side walls, you can see that the corner line where they intersect is common, and hence we can say that the side wall and the front wall are not orthogonal to each other. So let us consider an example over here of the orthogonal subspace. So if we have a V, a vector space V in plane, V is a plane which is spanned by small v1 equal to 1, 0, 0, 0, and v2 is equal to 1, 1, 0, 0. If we have another vector space W, which is a line spanned by W is equal to 0, 0, 4, 5, then W is orthogonal to both the V's. So that means V1 and V2. How? 1 multiplied by 0, 0 multiplied by 0, 0 multiplied by 4, 0 multiplied by 5. If you add up all that, we are going to get a 0. So that is V1 transpose W is equal to 0. Similarly, V2 transpose W is also equal to 0 because 1 multiplied by 0, 1 multiplied by 0, 0 multiplied by 4, 0 multiplied by 5, all added together are going to give us a value 0. Now, this V is a plane which is spanned by two different, vectors, V1 and V2 over here. And this W is a line which is spanned by the, what you call, vector, which is W over here. So the line W will be orthogonal to the whole of V. We see that the line W is orthogonal to the whole of V. So the dimension of this is, if you see over here, this is a four-dimensional quantity. This is a four-dimensional quantity. So on the whole, we have all these are part of the vector space, which is R to the power 4. And the subspace V has a dimension which is 2 because it is spanned by two, what you call, it's a plane. Basically, it's a plane. The subspace V is a plane, and hence it is having a dimension of 2. And W is a line, and therefore it is having a dimension which is 1. So still, in addition to the two planes here, we still have a third subspace. There is a room for further third subspace because dimension of V is 2, dimension of W is 1, but R to the power 4 has a dimension which is 4. So therefore, we can consider another length L, which is spanned by Z equal to 0, 0, 5 and minus 4. And this is perpendicular to both V and W because if you take V1 transpose Z, V2 transpose Z, W transpose Z, all these will give 0 because 1 multiplied by 0 plus 0 multiplied by 0 plus 0 multiplied by 5 plus 0 multiplied by minus 4 is equal to 0. Similarly, V2 transpose Z will also be equal to 0 and WT transpose Z will also be equal to 0. That is because 0 into 0 plus 0 into 0 plus 4 into 5 plus 5 into minus 4 will give us 20 minus 20, and that will be 0. So then all the dimensions of V, W, L together will become the dimension of the total space, which is R4. So now the question will arise, what space is perpendicular to all of VWL? So V has a dimension of 2, W has a dimension of 1, L has a dimension of 1 because this is a line, this is a line, this is a plane. Now, in a space which is R to the power 4, all things are covered. So you can say that only the 0 vector is perpendicular to all this because we have already written in the earlier class that 0 vector is orthogonal to itself and orthogonal to every space in R to the power n. So therefore, we can say that the 0 vector is the one which is perpendicular to V, W, and L. So now we come to the fundamental theorem of orthogonality, which states that the row space is orthogonal to the null space R to the power n. We have considered four spaces. Four spaces we have considered: the column space and the left null space, the row space, and the null space. So we see that the fundamental theorem of linear algebra and fundamental theorem of orthogonality states that the row space is orthogonal to the null space. They are perpendicular to each other, and the column space is orthogonal to the left null space. So the row space as well as null space are in Rn, that is, their dimension is n, and the column space and the left null space will be in Rm. Together, the null space will be what you call the column space and left null space together will be in R to the power m. They are part of the subspaces of R to the power m. So this just gives us the dimension of the row space plus the dimension of the null space is equal to the dimension of Rn, that is equal to m. Similarly, the dimension of column space will be R, and the dimension of, that is the rank, and the dimension of the left null space will be m minus r. If we add them together, we will get the dimension of the space, vector space, which is r to the power m. And the proof of this can be considered something like this. If x is in null space, then ax is equal to 0. If x is in null space, ax equal to 0. If v is in row space, it is a combination of the rows v equal to atz. If v is in row space, it is a combination of rows v equal to atz for some vector z. So therefore, we can say that the for null space to be perpendicular to row space, the value of Vtx should be equal to 0. The V transpose x, and V is nothing but A transpose Z here. And you can write over here A transpose Z, the transpose x equal to, so if you have xy whole transpose, then that will be equal to y transpose x transpose. So therefore, if we have xy transpose, then that will be equal to y transpose x transpose. Therefore, we can just try to write this as z transpose, this z transpose, and a transpose transpose, which will become a itself multiplied by the x. So now ax, we know, we have written already ax here equal to 0 because x is in null space of ax. And therefore, it will be z transpose into 0 vector, and that will correspond to a 0 vector. So thus, we can say that null space is perpendicular to the row space. V transpose x will be a null value. So suppose, let us take an example for the same. Suppose A has a rank 1. So its row space and column space are lines. Rank 1 matrix A will be 1, 2, 3, and 3, 6, 9. The reason why matrix A has rank 1 is the second column is the multiple of the first column. Also, the first row, the second row, and the third row are multiples of the first row. Okay, so they are dependent. The rows are all dependent and the columns are all dependent. So therefore, the rank of the matrix is only 1. So the rows are multiples of 1, 3. The null space contains x equal to, so because it is 1, 3, the null space naturally will consist of minus 3, 1, which will be perpendicular to 1, 3, which is orthogonal to all the rows. So the null space and the row space are perpendicular lines in R square. So we should take the null space, so to say, transpose multiplied by the value which is what you call the row space transpose, the null space, sorry, the row space transpose uh, multiplied by the null space will give us 0. So we will get here A into what you call, so to say, the value of the null space will give us 1 3 multiplied by this 3 minus 1, 2 6 multiplied by 3 minus 1, 3 9 multiplied by 3 minus 1. All these are going to give me 0. That will give Ax equal to 0. In contrast, the other two subspaces in RQ. So the other two subspaces, when we are talking about the column space and the left null space. So these will be in RQ, and the column that corresponds to here, what you call N. So the column space is the line through 1, 2, 3. 1, 2, 3. So number of rows will be 3. The left null space must be the perpendicular plane y1 plus 2y2 plus 3y3. And that the equation, that equation exactly the contents of y transpose A. So this equation is exactly the contents of y transpose of A. So y transpose of A is, what you call A, which is there here as it is, and then y transpose will become the left null space corresponding to the left null space, and that might be 1 1 minus 1 as the value of y. So 1 1 minus 1, and that will give us the value which is 0. Then we come to, there is another thing which is the orthogonal complement. Now let us see what this orthogonal complement is and try to understand it with respect to how it is different from just orthogonal. So given a subspace V of Rn, the space of all vectors, so here it is very important to consider all vectors orthogonal to V is called the orthogonal complement of V. Okay, the space of all vectors orthogonal to V is called the orthogonal complement of V. So here the dimension of all vectors are present here. It is denoted by V, the symbol for perpendicular, and that is known as V perpendicular. So here we have some theorems, which is V perpendicular is the subset of R to the power n, and span of V perpendicular is equal to V perpendicular. V perpendicular will equal to the span of V, and theorem 4, which says V perpendicular is equal to V, and V intersection V perpendicular will be equal to the 0 vector. So if some vector is present in V, okay, if some vectors are present in V, the vector space V, vector subspace rather V, then in the what we call vector subspace V perpendicular, whatever is not present in this should be present in this. So that is why we say intersection of that will be a 0 vector. So that's why all vectors which are not there in V, okay, in a particular space Rn, will be present in V perpendicular. That's why their intersection will be the 0 vector. So the null space is a orthogonal complement of the row space. If something is present in what you call an A that cannot be present in the what you call CAT, that will just correspond to the row space. Okay, so because of the reason that the dimension of the what you call null space, the dimension of null space will be naturally the value which is equal to m minus r, and the n minus r, and the number of the what you call dimension of column space will be r. If you add up both of them, that will become n. Similarly, so that just gives us dimension of the row space plus the dimension of the what you call null space will be equal to the number of columns. Similarly, we have every vector orthogonal to the null space will be naturally in the row space. So whatever is not there in the null space, that will be there in the row space. Every vector orthogonal to null space will be in the row space. So Again, this is just the opposite, or you take the what you call uh, twice the once more you take the perpendicular on both sides, you're going to get this. So the same reasoning applies to the A transpose, and this produces the dual result, that is the left null space N of AT and the column space CA are orthogonal components. So what does this give us? This just gives us that the dimension of the left null space plus the dimension of the column space will give us the number of rows, will give us the number of rows. So the fundamental theorem of linear algebra says the null space is the orthogonal complement of row space in Rn, and the left null space is the orthogonal complement of column space in Rm, where A is a m by n matrix, where m is the number of rows and n is the number of columns. So two matrices V and W can be orthogonal without being, it's always possible that two matrices V and W, they can be orthogonal without being the orthogonal complements of each other. For example, the line V spanned by 0, 1, 0 is orthogonal to the line W spanned by 0, 0, 1. But V is not the, so to say, W perpendicular. That is only because of the reason that the dimension of the line V is 1, the dimension of the line W is 1. If you add them up, we'll get 2, whereas the dimension of the vector space, which corresponds to whose subspace V is, there we have R cube, because we have 3 terms over here. So this is in R cube. So R cube will have a dimension which is 3, and hence 1 plus 1 is not equal to 3. Therefore we can always say that the two matrices V and W are orthogonal, but they are not orthogonal complements of each other. So the orthogonal complement of W is W is a line, and the orthogonal complement of W is a two-dimensional plane, and the line corresponding to V is only part of the what you call W perpendicular. So when the dimensions are right, orthogonal subspace are necessarily orthogonal complements. So if W is equal to V perpendicular, then V is equal to W perpendicular, and then we say that the dimension of V plus dimension of W will be equal to n. So splitting Rn into orthogonal parts will split every vector into x equal to V plus W. The vector V is the projection of x onto the subspace V. The orthogonal component W is the projection of x onto the W. So the orthogonal component V is the projection of x onto V, and the orthogonal component W is the projection of x onto W. So this is what it shows, that row space is rather orthogonal complement of null space, column space is orthogonal complement of left null space. So if you have a vector xr in the row space, if you have a point in the row space, this is mapped to a point in the column space, okay, of the matrix A, for a particular matrix A. The row space of A, if we have a point in the row space of A, then that is mapped to a particular point in the column space of A by means of AXR plus B. However, a point which is outside the row space also can be mapped to the point in B, because of the reason that if we take x equal to XR plus XN, and AX will be equal to B also. AXR is also equal to B, AX equal to B, where XN is equal to 0. But if we take a point in the null space, then that is mapped onto the 0 vector. Nothing is mapped onto the left null space. No point here is mapped onto the left null space. So you can see that And all the points here in the null space are mapped onto the zero vector. The points here in the row space, every point in the row space is mapped onto the column space, and vice versa. Naturally, that will be vice versa also. So naturally, every point, the row space points and column space points are invertible to each other. But however, if we take here the point outside, you cannot be invertible because you don't have it in the row space at all. It is added to the two components here. One, special solution and one particular solution, so to say, corresponding to the pivot and the special, what you call pivot, as well as the free variables. And thus, we will get here this point. Also, there might be a point here which is mapped onto the column space of A. The dimension of the row space is R, and dimension of the null space is n minus R. The sum of those two is n. Similarly, the dimension of the column space is R, and the dimension of left null space is m minus R. The sum of them is m. So all that is, again, same things is explained over here. The null space is carried to the zero vector. All the points in the null space are carried to the zero vector, mapped onto the zero vector. Every ax is in the column space. So every point which is what you call ax will be in the column space. Whether it is in row space or outside, will be in the column space. A typical vector x has a row space component and a null space component. X has two components, row space as well as null space component, which is x equal to xr plus xn. When multiplied by a, then this will just give you ax equal to axr plus axn, and the null space component goes to 0, axn goes to 0, and axr will go to the column space. So together, ax will go into the column space plus the null space will give the column space itself. So the row space component goes to the column space. The row space component goes to the column space, and that is written by axr is equal to b. So everything goes to the column space, whether it is there in the row space or not, it goes to the column. The matrix cannot do anything else. From the row space to the column space, A is actually invertible. So that means here, whatever is there, a point here is mapped onto this, and a point here is mapped, inversely into this. Only one point in the row space. One point in row space is mapped to B, and one point in B is mapped to the row space, vice versa. So that is why we say that it is invertible. A is actually, that is, every vector B in the column space comes from exactly one vector xr in the row space. So with this, we come to the end of this particular lecture, part 3. Thank you.